events. I was also very honored to be able to contribute to this big initiative. And I just simply hope that we can continue this wonderful initiative to promote the knowledge exchange with it of the students, scholars between different continents. It's always very difficult to talk after Professor Guo. He managed to make this room so hot and enthusiastic. So I then try to think a little bit about my talk. I will cool down a little bit from his talk. So I'll talk about that special application where fracture mechanics could really contribute. Is that how we can design the surface of the coatings which has a super low ice adhesion. For some of our colleagues from the tropical area, like South Europe or south part of the China, and probably you don't experience this icing problem. But I work in Norway, and originally I'm from northeast part of China. So I have a lot of experience about ice, about the coldness. Often people think that ice is so romantic, and there's a lot of movies and nice activities about the icing, about the ice and snow. However, that in the cold region, when we move to the Arctic, and what we experience is on the right-hand side. There are a lot of icing problem on the infrastructure, like in the aviation industry. Or for example, the example I show here is the world record. In 1969, the icing problem in Norway, in 1 meter of the power cable, it accumulated 359 kilogram ice. And the consequence is that it collapsed the whole power cable and the tower. Used almost like 2 months to fix all the problem here. And also like the signal tower for the mobile or other signals. When there is ice, and due to this different dielectric constant, and the signal reduction can be up to 90%. So it really influences our daily life. How we cope with the icing issue. Traditionally, we use those active de-icing methods. Why we call it active? Because we need to pump in the energy to remove the ice. And that's like a mechanical removing or the electrical heating, or use some chemical salts to melt the ice. Problem is that all this need a lot of energy input and also the labor working in those environments. And some maybe environment harmless. So the researchers and industry are thinking, can we also develop the passive anti-icing method? There we don't need to pump so much energy, and by the surface of the coating itself, tuning the interaction with water and snow and ice. Then we can reduce the effort to remove the ice. And from the water to ice transition procedure, we can have these 3 strategies to have the passive anti-icing. The first of all, course, if we can help carbon water, never have the water resource, then we never get the ice. Or if we allow the water condensate on the surface, but then we can delay the jobless waiting time. So provide time to the people operator to remove those water. But think about the 6 or 7 months winter in Norway. And anyway, that water will condensate on the surface. And anyway, in this long, cold winter, and they will form ice. So probably the reality is that we have to deal with ice, but with the lowest ice adhesion. So if we have surface of the coatings, and that can easily remove the ice by its own gravity or by natural wind. And that's also a win case. So my talk will follow this outline. And first, I'll just have a recap of adaptability and the suprahydrophobicity. Other people are familiar with those. And then to introduce the ice phobicity, how we can define that, and can we quantify the ice phobicity. Then introduce our strategy based on our fracture mechanics knowledge, propose that is the macro scale crack initiator mechanism, and enable this super low ice adhesion surface. Then give you some examples of our developed anti-icing surfaces, and then the take-home message. Yeah. talking about wettability concept, it has been there for more than 200 years. And the definition is very clear. It's just the force balance at this three-phase contact corner here. That's just the force balance between the solid, liquid, and vapor phase. Then we have this contact angle theta to quantify the wettability. When it's below 90 degrees, then we call it a hydrophilic, the surface lack water. When it's above 90, then the surface heats the water. We call it hydrophobic. And nowadays, it's very popular for the people to study the superhydrophobicity. And there, then not only the surface chemistry itself will have the higher contact angle, we also need the surface structuring. This joint effort will make the contact angle over 150. Then we call it superhydrophobicity. And in the biomimetics field, it's so popular to study all this biological surface and to have the super high contact angle to reach this superhydrophobicity. So in long time that people think, okay, probably we can use the similar concept of superhydrophobicity to define this ice phobicity. But now the question will be that we have this three, like the strategy to repel the ice, to have this passive anti-icing. So which one we should use to quantify the ice phobicity? So we see here, if the first one, the surface should always repel the incoming water, then it's just as this superhydrophobic surface with super high contact angle and with any tilting or the impact to the surface, and a water droplet will slide down automatically. However, the researchers have shown that even in very short time, in high vapor pressure case, that a tiny water droplet, and they will just condensate in the pocket of those surface structure, and then form the ice with an even lower temperature. So the superhydrophobicity doesn't really work for the ice phobicity. Also, a lot of people focus on the delaying this droplet freezing. They design different surfaces, and by tuning the heat transfer between the surface and the top water droplet, and then to delay the freezing time. And so far, the state of the art of those surfaces can delay the icing time is around maybe 7,000 seconds, and that's approximately 2 hours. And that's also not work in the long winter. So the only left is actually lowering the ice adhesion. And repeat again that we have to maybe live with ice, but with the lowest possible ice adhesion. So how low is low enough? Some of the colleagues may work on the ice itself. So the ice itself, bulk ice, has the tensile stress up to maybe 3 megapascal. And the typical metallic surface, they will have ice adhesion larger than 600 kilopascal. While those composite surface with only surface modification, not surface structuring, they approximately have the ice adhesion down to 160 kilopascal. Here is the research about that. In the
start of the conference,
the researcher tried to study how the ice adhesion correlation with the wettability. With those non-structured surface, the maximum contact angle we can get is 120 degrees. And the lowest ice adhesion we can get is around 160 kilopascal. If we want to reduce the ice adhesion, increase the water contact angle, we have to do the microstructuring. So based on those, our group have defined this different concept. The ice-phobic surface, which should have the ice adhesion below 100 kilopascal. And the low ice adhesion surface, which should below 60 kilopascal. This is based on the requirement from the US Navy. They were looking for the low ice adhesion surface. And later, we even reduced this value to the 10 kilopascal and name it super low ice adhesion surface, in short, SLIA. The physical meaning of SLIA is that if we have 1 cubic meter ice cube here. And if we do it vertical sharing, and by the ice its own weight, if they can fall by their own weight, then the maximum shear stress we have at the interface is this 10 kilopascal. So we set our goal that the ice adhesion 10 kilopascal, and to see how we can realize that. And if we have a simple model here, ice cube on the surface, then we have this horizontal shear, and from the fracture mechanics concept, that the shear stress is proportional to the square root of the interface elastic modulus and the surface energy. So a lot of researchers or the works have focused on the reducing the elastic modulus and decrease the surface energy. However, in this model, we see there is one more term at the bottom here is the total crack length. So our group, since we have long experience with the fracture mechanics research, so we focus on how we can maximize the crack length. So it has same effect as reducing E and G here. And this is our focus. So we proposed this multi-scale crack initiator for molded surface. How to realize that? Let's see. So our goal is clear to reach this 10 kilopascal ice adhesion. And then we see the water viability correlation with ice adhesion with only the surface modification. Then we actually tune just the surface energy. And we break the bonding between ice and the surface at the atomic scale. So from the fracture mechanics, we can call this nanoscale crack initiator. And it has the minimum value around 160 kilopascal. If we want to further reduce ice adhesion, we have to introduce the macro structuring. So we call it a macro scale crack initiator in short MISI. And the problem is that the MASI and NASI and MISI, they have to work together and they have a linear discorrelation to reduce ice adhesion. But think about that, if you have an oil platform with the runway for the helicopter, and it's probably 150 meters long, how you can do this NASI and MISI on those surfaces. So we definitely need a new strategy to reduce the ice adhesion. And we hope that we can reduce it from any point along this curve. Here, then comes our proposal, this macro scale crack initiator. And different from NASI and MISI works on this interface between ice and surface. Now we work on the subsurface structure. We try to introduce subsurface structures into the surface. Then we maximize the deformation incompatibility between our surface and the ice cube. Then we can reduce the ice adhesion. And at the same time, since we leave this interface free, so this MASI can be easily incorporated with NASI and MISI. And if we see a little bit of this zoom in of the MASI, we have just the one unit volume with this subsurface macrostructure. And we have water here, and when the ice formed at a low temperature, and when we try to remove ice, we create this kind of like a VV surface deformation, and it create this interface cracks. And I don't have only single crack. I probably have multiple crack initiation sets. So in total, that I maximize the interface crack length and reduce the interface adhesion. So this is our design principle. Then let's see some examples using this concept and how we can realize this MASI and multi-scale crack initiator mechanism. And here is mimic the pomelo peel. And now is the season. I know in China it's the season for the pomelo. And if you like it, ever peel this pomelo, and you probably feel there is the outer layer surface with this a little bit wax and a little bit contact surface, and inside is very porous and soft layers. So inspired by that, we designed this the three-layered the silicone sponge. We have top and bottom surface, which is smooth and compact, to protect the middle layer, while the middle layer is porous structure to provide this massy effect. So the middle layer is responsible for mechanical compliance, and top layer is protecting the middle layer from water or the ice invasion. And then we can see it's a very nice result that with this cyclic de-icing test, we can have very stable ice adhesion, about 1 kilopascal. So the echo Professor Guo's talk that we really care about the durability of the material and how they work in long term in the operation conditions. And another example I want to show you is since we have this kind of like the substructure design. So in the same time, we can also play those substructures with some refillment. And here is the substructures filled with liquid lubricant inside, so that this liquid lubricant could diffuse into the interface. So in parallel with the macro scale crack actuator, we also have lubrication at the interface, will further reduce ice adhesion. And here I choose really extreme liquid lubricant. It's the ethanol, because the ethanol has the freezing temperature at minus 126. So at a very low temperature, like in Arctic operation, the material design temperature is minus 60, and it will still keep the liquid state. And this is just a mimic all this like the frog or other like the animal which have this very sticky lubricating surface. And this is just a secret from the gland in their skin. And the results is really nice. And we can see that ice adhesion dramatically reducing with increasing the ethanol content. But then you probably will have the question, because the ethanol is so easy to evaporate. So what is the stability of the material? So we monitor how this evaporation of the ethanol in the material. And here you can see that in the first 10 days, the evaporation rate is quite high, but then it reaches stable. It reaches this dynamic equilibrium. So then we can hold actually the ethanol there for quite a long time. And we monitor it more than 200 days, and it reached really stable status. Yeah, the next example is that in addition to those liquid lubricants, because it's probably easy to deplete with removing icing process. So can we also have other type of lubricant? And here is an example that we use the solid lubricant. It's the peanut oil. And the feature of that is above 3 degrees, it will be liquid phase. But it's below 3 degrees, it will be solid. But it still have this small lubricating molecules. So the depletion rate of those solid lubricant will be much slower than the liquid lubricant. And here the red curve is that with this is the solid lubricant, and we can see that the ice adhesion is below 5 kilopascal, so it's still in the SLIAS range. And also in this the cyclic test process, we did 30 numbers of cycling icing de-icing tests, and the ice adhesion is stabilized at the end at around 16 kilopascal. So it's still very low, acceptable, the ice adhesion surface. Yeah. In addition to those examples I show you, we also work on all different those strategies to lower the ice adhesion. For example, mimic the human skin. When you sweat, you have a lot of salt and ions, and also the ionic gel surface, which will melt the ice at the interface and change this solid-solid contact to solid-liquid-solid, and dramatically reduce ice adhesion. Also, we introduced the self-healing properties into the system, so that if there is any mechanical or the chemical damage, the material will itself cure and then repeat this recover its functionality. Especially here is an ultra fast self-healing process. With 30 seconds, it will recover to its full function. Also, like other types of those biomimetic onion-like surfaces, or in some application case, we need to have this multifunctional coating. For example, those outdoor camera, you have to be transparent, self-healing, anti-icing. So we incorporate the different functions into those one surface and to see how it will work efficiently. Yeah. So far, this massing mechanism we proposed for low adhesion has been very successful, and we got a lot of attention from the field. However, we are also facing some challenges. We are using this fracture mechanics-based model to reduce adhesion and by maximizing the deformation incompatibility. But then, in the same time, it's basically just a soft material. So we have the problem of the low cohesion strength of the surface. And also, if this surface has very low adhesion with ice, it also means how low adhesion with a protected surface. And also, like durability issue, we need functional durability, mechanical durability, environmental durabilities of those surfaces and coatings working in extreme conditions. So we are also developing some potential strategies to cope with all these challenges. For example, if we can have the particle reinforced composite, it remains this functional property, but in the same time, reinforce the mechanical properties of the surface. Or we could have maybe the hard 3D network contains this soft coating, in a way also strengthening the material. Or maybe those functional graded surface with holes, with particles, with any other design, so that we will have maybe one part of the surface have low adhesion with ice, but the other part has strong adhesion with protected surfaces. And if you have any new ideas, and welcome to talk with us. Yeah. So take home message and make it very quick because I got this task from our chairperson to save some time. So based on our fracture mechanics knowledge, we have developed this anti-icing design strategy. So different with the traditional strategy, focusing on the interface here with the reducing surface energy and surface structures. We focus on the subsurface structures. So based on that, we propose this macro-scale crack initiator mechanism, which maximizes the interface crack length by increasing the deformation incompatibility or the stiffness mismatch. And it can be easily incorporated with any other strategies. And then, based on our strategy and mechanism, we have prepared different types of those super low adhesion surfaces with adhesion below 10 kilopascal. At the end, that this design strategy can be easily extended from the anti-icing application to other types of this solid contact problems. Yeah. Okay. So with a winter picture of our main building at NTNU, and I would like to thank all my collaborators, funding partners, and thank you for your attention.